So we started with an introduction of kind of math, basically linear systems and Fourier transforms, and in particular we applied those to a very kind of classic problem of mass on a spring. And we showed how actually using linearity and the superposition principle we were able to solve that differential equation in no time in the frequency domain. Later we showed that from the displacement in the frequency domain you can actually come up with a meaningful optical description of the material. Going from a microscopic level where we induce dipoles through the electric field of the applied optical field. We induce dipoles, we average those, we obtain a macroscopic induced polarization, and that's basically what relates to the refractive index. The epsilon to chi and finally to the refractive index. And from this very basic kind of model, the Lorentz model, we were able to draw the curves for refractive index, both the real part and the imaginary part. So in other words, the absorption lines and the refractive index as a function of frequency. And we discussed those a little bit in detail, what happens below the resonance, what happens after the resonance, around the resonance. And we decided that if we want to have a transparent system, we better be below the resonance, right, or at least outside the resonance. And we also found something very funny, that around the resonance we have dispersion that's negative. The derivative of the refractive index with frequency is negative, which among other things tells us that the group velocity is higher than c, but that should be okay. There should be no contradiction with Einstein. Okay? In any kind of imaging that doesn't in any kind of imaging, there are two main concepts. One is resolution. That means how small a detail can we solve in the sample. And from the experiment with the CD-ROM and so on, we kind of established that these angles that we collect from the sample limits what we can image in terms of resolution, limits the resolution of our imaging to something like λ/2. One lecture by Professor Carney today was aimed at telling you that actually if you go to near field, to the evanescent fields that we discussed yesterday, you are not limited by λ/2 anymore, and actually you can resolve much finer details. Probably you know that super resolution microscopy is a very hot field nowadays, and we are going to have some lectures about it, where the push is to go beyond the λ/2 resolution even in far field. And the trick is to use, maybe instead of linear optics, use some kind of nonlinear optics. So there are two concepts again in imaging. One is resolution, the other one is contrast. And last night we've seen a very strange kind of a contrast mechanism. But deep down actually the contrast is given by absorption. So the light is absorbed in tissue and there is a sound wave that is generating due to this absorption, due to local changes in temperature, and the detection is done through the ultrasound detection. But you can have other types of contrast. In fluorescence, basically what you are detecting, you're first tagging your structure of interest with molecules that emit light. So that's kind of the opposite of absorption. You're looking at some kind of emissivity, how much light is emitted from the sample. Both of these are actually something to do with the imaginary part of the refractive index. Okay, absorption and emission, they're kind of a sign, opposite sign of one another, but they have to do with n double prime. However, there is contrast to be gained from n prime. That means from the refractive index, the real part of the refractive index, from the part that actually makes the sample scatter. And we call that that belongs to the type of intrinsic contrast imaging, in the sense that we don't need to add anything to the cells or to the tissues. We're just trying to reveal the optical properties of the tissues and cells as they are in nature. So kind of broadly speaking, the amplitude contrast mechanisms have to do with, the absorption mechanism has to do with the amplitude of light. You're looking at how much attenuation or how much gain you get from the sample. while the scattering mechanism is something, it is encoded in the phase. So that's why without tagging you don't see the cells very well, just because they act on the real part of the refractive index, not so much on the imaginary part. In other words, if I write my plane wave as e to the I n prime k naught z, and then the imaginary part gives me two i's, which will give me a minus n double prime k naught z. You see, this gives me an attenuation. This gives me a phase change. And when the detector comes in and measures the modulus square of this, that's the reason that the phase information goes away. That's the reason that the cells are so transparent and you don't see them unless you tag them or unless you do something smart with the phase to reveal those details. So phase contrast microscopy is one of the methods that actually enabled to get the phase information, couple it back into the amplitude. So get this M prime information and put it back into some kind of amplitude modulation. And that's why phase contrast microscopy is such a successful and commonly used technique in pretty much all cell biology labs, because you can just look at cells without tagging them, without attaching any exogenous contrast agents, and you see details from within the cells. And that's the reason it earned the Nobel Prize in 1953, I think, for physics. And this was invented by Zernike in the 30s. So you see, I'm trying to get closer and closer to scattering mechanisms. And another talk by Professor Carney was on scattering and actually doing a 3D reconstruction based on scattering. So keep in mind, if you look at the history of microscopy, resolution is one concept that was pretty clearly cut. The contrast mechanism, it's probably been what's been driven the microscopy field for more than for hundreds of years. In other words, people are always coming up with new ways of generating contrast. Recently there was a Nobel Prize on GFP, green fluorescent protein, that basically takes kind of, with this technology you make the cell naturally produce a protein that's fluorescent. So in a way it's combining exogenous contrast agents, usually the fluorophores. Now you are making kind of intrinsic contrast. So make the cell generate that fluorescent protein. But there are many, many methods that have been developed, dozens of them, with the specific aim of improving contrast. Okay? And in there we want to have it less destructive, less kind of affecting the cells, non-invasive, basically. So scattering is very good for that, except that you need to work to do some kind of trick to get to the phase information. So more about that, hopefully, in Dr. Carney's talk. The dynamic light scattering talk that we're going to see now is related to this problem, and it's actually a very powerful technique that was developed in the 60s, and among other things allows you to, if you have a scattering sample that is also dynamic, by using light, scattering light from this dynamic system and measuring time-resolved signals, an intensity that fluctuates, scatters and also fluctuates in time. Measuring this allows you to extract information about either the particle size, the size of the scatterers that emitted the light, if you know the medium, or the other way around. If you know the particle dimensions, particle properties, you can extract information about the surrounding medium. And there are many commercial products that they're called particle sizers. And the interesting and exciting part about it is that you can size particles that are much smaller than the wavelengths of light. You can particle size, you can do particle sizing on scatterers that are 1 nanometer or 10 nanometers. And I'm going to show you why that happens. This has to do with the fact that the information is not in the angular distribution, not in the k vectors, but it's in the time signal. Okay? So after this long introduction, let's see what dynamic light scattering is about. So this is your medium. So it's let's say it's a suspension of particles, and they're basically fluctuating they're in a suspension, and they are at thermal equilibrium, and therefore they are moving. In order to understand what's happening in this system, I come in with a plane wave with the incident wave vector k incident, and I am observing the scatter field somewhere at the point P in far field. The basic idea is that at this point P, you should probably make it farther away to kind of suggest that we are in the Fraunhofer approximation, which we discussed yesterday. So at this point P, I have basically interference from all these fields coming from all the particles, right? So each particle becomes a kind of a secondary source of light, and so on. Everything adds up here. And do you remember when we talked yesterday about the Young interferometer with two particles like this? So I come in with the K incident, and then here I think we learned that this thing is going to have a certain envelope due to the diffraction of a single hole, and then there will be some modulation due to the shift property. If you remember, it will be a cosine of something to do with the distance between the two, and there will be a cosine modulation on top of this whole thing, kind of like this. So imagine that this axis, you can think of it as angles, right? This is where far away from these two particles, or these two apertures. The distance is z. So this basically is spatial frequencies, but it is equivalent, is proportional to angles, right? So I'm looking at 0 angle, I get the maximum, and then higher angle, less, 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 and then it starts to oscillate as I go this way. So imagine now that I place my detector here at this point. So I'm looking far field, and my detector is right there. Probably I don't need this, right? So my detector is at a particular angle. What will happen if the distance between the two apertures starts to fluctuate? What do you think is going to happen? Basically, I'm going to have a cosine that is changing period, right? The period of the cosine is related to the distance between the two. So imagine this is kind of randomly fluctuating. That means the cosine is actually randomly fluctuating. So basically, it's safe to say that if my detector is sitting at one point, it's going to see this cosine moving around. Basically, it's going to give me a signal that fluctuates like this. Random signal. But you get the intuition that by measuring carefully that fluctuation, I should be able to back up this distance. Somehow. They are related, right? Well, that's the spirit of dynamic light scattering, except that now the problem is slightly more complicated. I have a bunch of these holes, and they're not really holes, they're particles, but the idea is the same. I have all this interference from all these particles, and as in any interference, the phase difference is what matters. And you see the distance between, relative distance between the particles is what gives you the phase shifts. So if these are under Brownian motion, these particles, these phase shifts are going to fluctuate randomly. Therefore, the intensity at this point here is going to fluctuate in time randomly. So what we're trying to do now is to see exactly how can I go from a measurement of fluctuating intensity to extract some information about the particles. Let's say I'm most interested in the size of the particle. Okay? Are we okay with this so far? That was the question I had? Great. Okay. Now, first I would like to be able to write the distribution of refractive index in space. Okay? So I will assume that the particles are identical for now. It can be extrapolated, but let's start easy. So I have identical particles that they are characterized by this F naught is called scattering potential, but basically F is proportional to n squared minus 1. Okay? So it's like your chi. So how can I write down the scattering potential or the refractive index distribution if I have a bunch of identical particles distributed in space? The best way to write that is to use the properties of the delta functions. And the one property of the delta function that we also used yesterday is that if I convolve any given function with a delta function, if I do the convolution, it's going to take this function and place it at the position of the delta function. Okay? You know this, right? Convolution of f of x times delta of x prime minus x dx gives you f of x prime. So if I convolve a function with a delta that is shifted by x prime, it's going to take this function, it's going to put it at the position of the delta function. Okay? So basically, I'm using this property to say that the distribution of particles in space is taking this particle and convolve it with the delta function at this position, and then at this position, and at this position. Delta function in 3D, imagine they're infinitely small dots, right? Such that the integral over the volume gives you 1. Okay, so I take this particle that has a certain diameter or a certain shape, let's say it's spherical, and I convolve it with the delta function here, and the delta function here. The delta function wherever the particles are. So one way to write this is like summation of delta of r minus rj, where rj is basically the position of all these particles in space. The trick is that the position is fluctuating in time. Right? That's where the information is. Roughly speaking, what we're after is this. KBT is the energy, the thermal energy that kind of governs the whole thing. So if the energy is fixed, if you give me a small particle and a big particle, which one is going to move faster? Small one, right? So that's the idea. I know thermal equilibrium, somehow smaller particles should generate faster fluctuations than bigger particles. Another thing is if I take identical particles but I put one in water and I put one in honey, which one is going to move more? The one in water, right? Or in air, even better. It's going to be faster. So this is the idea. We want to connect these, how these fluctuations of the scattered light, we want to connect these fluctuations to either the size or the viscosity of the medium. Okay? It's going to depend on both. So that means that how this vector position, this displacement happens in time, basically all the information is in there, in this displacement as a function of time. Okay? All right. If I take the Fourier transform of this, you see whenever I have a convolution, I tend to do a Fourier transform. Right? Just by default, that should be your approach. If I take the Fourier transform of this, basically it's your diffraction problem. Remember our DVD experiment? If I take the Fourier transform of this refractive index distribution, I get the diffraction pattern. It's the same idea, except that now my volume is 3D. So it's kind of a 3D diffraction problem. That's basically scattering. Okay? To me, diffraction is scattering compressed in one dimension. Okay? So if I take Fourier transform of this refractive index distribution, I'm going to get the angular distribution of the scattered light, except that now is in 3D. Now, what's going to happen if I take the Fourier transform of this? I'm going to take the Fourier transform of this, and the convolution will become a product, right? Right? I think we have that right there. Fourier transform of a convolution is a product. And now, what's the Fourier transform of this delta function of r minus rj? Well, you know the shift theorem, right? So the Fourier transform of a shifted function is the Fourier transform of the function unshifted times e to the I some phase, right? Now, what's the Fourier transform of delta? 1. So the Fourier transform of a shifted delta will be 1 times e to the I something. So you see a shifted delta gives you only a phase term, which is exactly kind of, we know the physics. The reason is that, let's say I take this particle and I move it here, all that this is going to do is going to do a phase delay by this much, let's say. right? When you do the Young interferometer, shifting these particles this way is going to add just a phase delay to your far field pattern. So mathematically, that's where it's coming from. So Fourier transform of this will be Fourier transform of F naught, which this is the refractive index distribution of a single particle. So that will give me how a single particle scatters if it was by itself, times a summation of V to the I K Rj, something like that. Okay? That's what we have here. Except that instead of K, we use Q. Okay, I'll give you a minute to absorb that. So basically, I come in with the K incident, and now this is the volume of scatterers, right? I have the scattered light, let's say, this way. Q is the difference between the two. K incident, K scattered. Q is the difference, is this vector here. So you see that this Q is actually, if I come in this way and I measure this way, Q somehow takes care of, tells me what the what the angle is, right? Okay. Basically, this is proportional up to a constant that we don't care about. This is what the field is going to be far away from my dynamic scattering medium. Okay? Yep.
So Q is a function of time?
Q is not a function of time. Q is just the difference between K incident and K scattered. K scattered is where I choose to observe, where I choose to put my detector. What changes is Rj, the coordinate of the particle. Right? Okay? So Q is, I pick Q, that means I picked an angle, and I pick to put my detector there, that means I'm going to measure at this scattering angle, 30 degrees, let's say. We'll see how important that is. It's a knob you get to choose. It can make your signal faster or slower depending on whether you take a large angle or a small angle. But we'll talk about that later. F is called scattering amplitude, but that doesn't matter. What this means is that it is proportional to the field, optical field, far away from the scattering medium. Okay, so we have this field, we have these phases in the field that vary randomly. Basically, if I take the modulo square of this, I'm going to get some kind of an intensity, right? That's what the detector is going to see. Because of the phases that randomly fluctuate, I'm going to get fluctuations in the intensity. How do I usually characterize a fluctuating signal, a random signal like this, of any kind? What do I do? How do I try to understand the time scales of the fluctuations? Autocorrelation, right? So you take a signal, you correlate it with itself. We defined yesterday what the correlation is, but basically you take this signal and then you shift it, multiply it with itself, take an integral of the overlap. So the slower it fluctuates, the more overlap you'll have. Okay? But if the signal is rapidly varying, only a little bit of shift will decay the overlap very fast. Okay? So right there, intuitively, you should have a feeling why autocorrelation is so useful. It gives you a time scale over which the signal becomes dissimilar with itself. Or in an opposite way, within the correlation time, the signal is quite similar with itself. It didn't have time to kind of fluctuate too much. So that's what we're going to do. We're going to do this correlation in this way, which is basically taking the signal, multiplying it with its conjugate at a delay tau. So this is t plus tau. And then we take the average. Okay, so this average is something to do with an integral. If you put the integral here, that gives you the definition of a correlation function. So basically, the rest is just calculation. I don't even think we should go to derive it, but I want you to kind of understand the physics. We have a fluctuating signal in far field that comes from the fact that the particles have a fluctuating coordinate, right? And how do I understand the time constants of these fluctuations? I'm doing an autocorrelation function. So I'm taking the field times the at instant t, I take the field conjugate at t plus tau, and I do an average. It's going to look like this. So now this sum, this is a constant in time, right? We don't really care. You know what the meaning of this is, F naught of Q? I told you a minute ago. So this is a particle as if it was by itself in the universe. You come with a plane wave, that's how it's going to scatter. It's going to look like F naught of Q. So we are safe. Professor Carney is here. So am I going to finish dynamic light scattering? Like 20 minutes and then?
Oh, I don't know. I'm going to have to come up there. Go ahead.
Okay. Thanks. So F naught is basically how one particle scatters. There is no time fluctuations of any kind. It's just simply the static scattering from one particle. So at best it gives you some kind of a envelope of the scattered signal. Let's say it's going to drop as you go to higher angles. But the interesting part is in the time fluctuations, right? So that's why when I take the autocorrelation function, this is going to become a double sum, right? So I take this multiplied by conjugate. This is going to give a negative sign here. So basically, this tells you in a certain delay time tau how much on average the particles are moving. Okay? So a small particle will move on average a lot more than a bigger particle. That's the idea. And of course the viscosity of the medium has to play a role too. If I put the same particle in honey, it's going to move less. Okay, so I think I should skip the details of the derivation. You can read it by yourself. Let me give you the result. Okay, so we need to evaluate this average basically, and we are done. But before we do that, I want you to realize that this is what we are calculating here is the correlation in fields. Optical field correlated with itself, but that's not what the detector is measuring. The detectors are measuring intensities. So the best I can do is to measure correlation in intensities. And what I'm going to show you now is that actually correlation in intensity, which we call G2, as opposed to G1, which is for the fields, G2 and G1 are related. Yep.
Wouldn't it be more useful to take like multiple points and measure the intensities of those multiple points and then try to, that way you could have systems and equations that you could solve?
Multiple points around the object?
Multiple points to measure from around the object.
At different angles?
Yeah.
What would that give you? Let's talk about it.
I mean, you have multiple receptors, and you could measure the intensity at one area, measure the intensity at a different area, and then, because when you measure intensity from one area, you get information about the intensity coming in from different areas of that area, but you don't get a full picture of where the light's coming from. But if you have multiple areas, then you can.
You're right. You're right if our goal was to reconstruct the 3D structure, and that's what Dr. Carney is going to tell you, I think. So in that case, you need more equations to reveal more unknowns. But in our case, we assume the structure is uninteresting. It's a bunch of identical particles moving around. What we want is their time behavior. So it turns out that for that, you only need to measure at one angle. Now, if you have a combination of many particles, so many different sizes of particles, then the time constants start to mix. And in that case, I think measuring again at different angles may help you. So it's true, measuring more angles gives you more data to work with, but if you are not into reconstructing the structure, you don't need to. Okay? Okay, so let's connect the intensity correlation function G2 with the amplitude correlation function G1. So G2 is simply the correlation, the intensity times itself, delayed by tau, average. So this is just the definition of a correlation. We normalize it such that we don't care about these constants. In general, anyway, your detector measures some weird stuff like volts, right? So you need to normalize it somehow. And I'll let you follow this calculation, but long story short, you find out that actually G2 and G1 are very nicely related, which makes it easier. Because otherwise, if all the information is in the amplitude, in the field correlation function, and you only have access to the intensity correlation function, and there is no connection between the two, we're done. There is nothing, we cannot solve the problem. But in this case, this relationship, which is called the Ziegert relationship, shows you that measuring G2, so G2 is measurable, you can get to G1, and we know that G1 is related to, let's say, particle size A, and maybe viscosity eta. Okay? So again, we measure G2, we get to G1, and then we get to the dynamic, the parameters of interest, size and viscosity. Okay, so how do we calculate this average now for G1? We were supposed to do this average, we left it here, we wanted to calculate this average. So unless you know the physics that governs the motion of the particles, you don't know how to solve the problem. Okay, so for instance, if you have particles that move in a flow, all of them at constant speed, you will get something for this average. If you have particles in Brownian motion in a complete viscous medium, you will get something else. If you have particles in a viscous medium that also has some elasticity, such as, I don't know, in a blood clot or in particles in a DNA solution, this will look yet different. So today we're going to solve the problem in the kind of the easiest, the classical case, where the particles are under Brownian motion in liquids. That means fluids that only have viscosity. Okay? So in that case, the equation that describes the probability of finding a particle at point in the vicinity of point R and time t is governed by the diffusion equation, which is this. Okay? If you're, what happened? Again, if your phenomenon is governed by a different equation, you have to use that, you'll get a different result. Okay? Now, the diffusion equation, I think we talked briefly yesterday, is different from the wave equation in the sense that we only have a first order derivative here, and that makes a huge difference. And the material parameter, the equivalent of that beta that we had in the wave equation yesterday, is the diffusion coefficient, D, which looks like this. The formula for D is due to Stokes and Einstein. And the diffusion equation, the diffusion coefficient relates, of course, to the temperature, to Boltzmann constant, but more importantly, it relates to the viscosity and the size of the particle. So that's what we are after. We're trying to measure these correlations of the scattered intensity and somehow get to A, the size of the particle. Okay? And because the information is encoded in the time fluctuations and not in the K distribution, in the angular distribution of the scattered light, this A can be sub-wavelength. In other words, you will be able to tell the size of the particles at the nanoscale, but you won't be able to tell where they are. That's what that means. Okay? Okay. So using this equation now, we are able to calculate the correlation function. And the final result is this. So the field correlation function for the light that comes from Brownian particles, governed by the diffusion equation, has this very simple expression. It's a correlation that decays exponentially in time. So we can write it like e to the minus tau over tau naught. We can call tau naught the correlation time. And that's where all the information is. Tau naught is 1 over dq squared. Yep.
Professor, what would change if the local temperature is a function of time? For example, cells are producing heat, so the local temperature would change.
Well, then I think you need to be careful. I think it complicates things a little bit. I've read papers where people are commenting, making sure that their laser is low enough in power so that doesn't happen. If it does happen, I think it's interesting. But there must be people who study this, I would imagine, in polymer science, in dentists, I would think. Dentists, when they cure with the UV light, who knows? But that would be interesting. So definitely things change. So your D becomes a function of time, right? This one. So roughly speaking, if the fluctuation times of the two, so the local temperature change is at a completely different scale than the time fluctuations of your particles, probably you're okay, maybe. So you'll end up with two time constants probably, so you'll have to decouple them somehow. But anyway, so this is a very nice but very simple expression, but it's very powerful. So all I need to do is I illuminate my dynamic, I get the glass of milk, and I want to measure the particles in the glass of milk. You know that the difference between homogenized milk and regular milk is just they broke down the particles into smaller sizes, right? So one way to test that the milk is good is to look at the particle size. One way to measure the particle size is to send a laser through it and look at the dynamics and measure the fluctuations. You want the fluctuations to be very fast because that means the particles are small. When I was a student, we are funded by Lockheed Martin to measure their nanoscale nanoparticles in suspensions that were used to polish wafers. So the final polish of a wafer that has to be perfectly flat, right, at the nanoscale, is to kind of send the suspension of very tiny particles and polish that in a wet environment. And the problem is that the particles tend to aggregate after a while and make bigger particles, and if that happens, they scratch the wafer and you have to throw it away. So it was a simple problem to find a way, send light in somewhere in a pipeline and measure that the particle size is okay. And this is a great tool to do that. So let's take a look at Q very quickly. Q is the scattering wave vector, right? So if I have the K incident here and I have the K scattered this way, that defines a certain scattering angle. This is my Q, the modulus of which is basically, if you look in this triangle, this is an isosceles. How do you say it in English? Okay, isosceles triangle. So that means this is 2 times K naught sine of theta over 2. Okay, this one. So you have two things in the Q. You have the wavelength and you have the angle. And look what happens if I change the angle. The higher the angle, the higher the Q. Right? It means that as I increase the angle, the correlation times gets shorter. That's nice. That means that, let's say you are limited by your detector in terms of acquisition time or something like that. And let's say you're trying to measure dynamics that's too slow, for example. That means I have this knob of modifying the angle, so I make the dynamic look faster. The idea is that as I look at higher angles, basically I'm probing wavelengths in the medium that are shorter and shorter. So for instance, this will probe this kind of wavelength, while this angle will probe the little one. The meaning of tau naught, roughly speaking, is the time that requires, the time on average that the particle takes to go over a distance of 2 pi over q. That's why the larger the q, the shorter that distance is, the shorter tau. Okay? Yep.
Is tau how many times you measure?
No. Tau is the correlation time of the fluctuation.
Okay. I thought
So-
tau 0 is the.
Oh, you mean tau, not tau naught?
Yeah, I mean tau.
Okay. So tau is the delay in the correlation time. So I measure a random signal, I measure the scattered intensity, I do a correlation, and that will be a function of tau. Tau is the delay that appears in the correlation.
Then how can you know the delay?
How can I know the delay? What do you mean? So I have a random signal. This is what I measure, right? My intensity versus time is going to look like this. Right? So then I generate the correlation function G2 of tau just by definition. It's integral of E of t plus tau dt. So you see, tau is the variable in the correlation function. Right? So it's the amount by which I shifted and then I integrate and so on. Okay, so from G2 we get G1. From G1 we get it equals e to the minus q squared d tau. Okay? So basically I will end up with an exponential versus tau. I measure its width, tau naught, and that will give me 1 over q squared d, and I'm done. Okay, so the information is in the width, how fast this decay happens. Yep? Okay, so let's do one thing and then we're done, I think. Oh, we have it right here. If you have a particle of 1 micron in water at room temperature, 300 Kelvin, the correlation time is a couple of milliseconds. So it means that if I want to measure 1 nanometer particles, I can, except that I need to measure very fast. Right? It's kind of a linear relationship. So that means I need to have a detector in the microsecond range, which I can, is no problem. And that will give you nanometer accuracy on the sizing of the particle. So that's powerful, right? It's actually very powerful. So you can size particles much smaller than the wavelength of light. Again, the idea is that the information is not in this K coverage, in the angular distribution of light. It's in the time constant, in how fast the particles are moving in space. So I can size the particles, but I cannot tell where they are. If I could tell where they were with nanometer accuracy, that would be breaking the law. Okay? Yeah.
So it's only work in a homogeneous medium.
So you mean what happens if my viscosity is changing in space?
Like what happens if it's non-homogeneous? Like one particle is bigger, one is smaller.
Okay. If you have a size distribution of particles, which is kind of always you do that. Basically, you're going to deal with the distribution of time constants, right? Each size is going to give you 1 tau naught, and so on. It's going to end up in a convolution, as usual, where the correlation function will be basically broader. So that's where multiple measurements come in, and I think there are commercial products that look into this too already. So you can measure at different angles, add more data, and somehow try to back that up. So Scott, is it okay if we take a 10-minute break too?
Sure.
Yeah. So one last thing I wanted to tell you.
It's required by the Geneva Convention.
Okay. One exciting application of dynamic light scattering, DLS, is to do microreology. This is a weird word, rheology. So rheology is the science of how things flow, basically. So you're trying to understand the viscosity and elasticity of fluids. Microreology is kind of doing this at the small scales. The main target being understanding the mechanical properties of cells. So nowadays it's kind of a hot subject to do this. Plant small particles inside the cell. Do the same thing that we mentioned about. So you illuminate them somehow, measure somewhere at an angle, let's say. Get the fluctuations in that signal. And try to understand now the properties of what's inside the cell. The problem is that the cells are not really like water. They are not pure liquids. Why? Because for one thing, they're full of these polymer networks, right? They're full of proteins. In other words, at the molecular scales, they have little springs that have the ability to also store energy, not only dissipate the energy. But with some special tricks, you're actually able to get both the shear modulus, the real part, and the imaginary part, which, believe it or not, is analog to the refractive index. The real part takes care of the storage of energy. The imaginary part is the dissipation, is the viscosity. So the field of microrheology is kind of hot nowadays, especially since there are some studies very recently that show that stem cells differentiate in various cell types depending on the stiffness of the mechanical properties of the substrate. Which means that mechanics is very important for cell function. People for the longest time thought that only chemistry is important. But it turns out mechanics and chemistry are connected. So anyway, DLS is a good way to measure that, to do that in cells. So not only get viscosity, but also elasticity. Get the whole picture. All right? So why don't we stop here? We take a 10-minute break, and then we come back. Yes?
It might be a very naive question, but the reason that you measure an angle is you don't want to get the excitation lines.
Yeah, and so what will happen if I measure at 0 degrees? What is Q at 0 degrees?
0.
Right. So it's funny. If you measure exactly at 0, if you measure the light that goes through unscattered, you get no fluctuations. There is no information. It's like in imaging. If you only measure the light that went through, you don't measure any scattered light, you can tell where the light came from. You cannot tell the structure of the object. Same thing in dynamics, yeah?
The correlation time that you measure contains information both about the size and the viscosity. Right?
Yes.
So in a DLS experiment, you need to know the viscosity to be able to determine the size or the other way around.
Yes. Most of the time, the commercial products are called sizers, so you know that it's something like water or something, and then you want to get the particle size. In microrheology, it's the other way around. You put particles of well-controlled size, and you're trying to get the material properties. Yeah, they come together. And they come in a product. You can't decouple them, basically.
And you talk about the case when the particles would have a certain size distribution, which is always the case.
Yeah.
If you had, say, a bimodal distribution,
that would be easier.
You can feed with a double export, or
Yes.
decay would contain the two-time constants.
Yeah, so that when you have 2 or 3 modes, you are going to get a kind of a, I don't know how to draw it properly, but in log it will be like this. It will be two exponentials. So that people do that.
Well, how about the light source is laser or just a regular lamp?
Okay, I didn't talk about that, but that's important. The most important characteristic here is the spatial coherence. I might have a sentence here or not. Okay. If let's say this is the volume of your scattering medium, if your coherence area is smaller than let's say your coherence area is about this size, then you have a problem. That means over patches of the order of coherence area, they're going to be you add them incoherently. What that's going to do at the end of the day is that your fluctuations are going to lose contrast. So as your coherence area gets smaller and smaller, you're going to see less and less fluctuations up until they're going to disappear completely. So the contrast of your fluctuation will be kind of the ratio of the coherence area over the whole, over the area of investigation. Ideally, you want to make this coherence area larger, so you don't need to worry about it. So that means any scattered light from any particle will add coherently with the rest of the fields. Okay? Is that okay?
Not a connected question, but we didn't really talk about properties of the particles themselves, and I'm guessing that might become more system basis. So,
You mean optical properties?
yeah. So assuming that we can say in general that all the particles or all the particles that we're interested in are the same
Yeah.
property levels,
Yeah.
then can you kind of shift this to a system where you're looking at a structure, say, cilia that are moving, and assume that the cilia is composed of a set of particles of a certain type, of a size that's smaller than the cilia itself, and then use DLS to track them?
Well, actually, we image some cilia in my lab. So there is information there, except that I think you asked several questions, but let's start with this one first. What happens if instead of a particle you have a chain? Well, the constants are different. Basically, if you have a chain, that's going to diffuse more slowly than if you have a monomer, a little particle. Okay, but that's been worked out in polymer science a long time ago. So you can do that. And actually, people measure these polymer solutions, right? You can do two things. You can plant particles in the polymer solution, which is easier, or some people are actually looking at the scattering from the polymers. And if they are big enough, you can see them with light. Usually, in the past, I think they used X-rays and neutron scattering. So it's a matter of modeling that process well, but you have some time information there, some dynamic information. And you also have said what happens if the particles are not identical. Oh, what happens if the optical properties are different, right? If I have a polymer particle and then I change it, not a polymer, a polystyrene, and then let's say I put silica particles, right? It doesn't change much. If the size is the same, the reason is that you see here, this is the scattering of a single particle right here. So that has no time in it. If you make it highly scattering, if you put a particle of higher refractive index, it will give you more signal. But in terms of the dynamics, nothing's going to change. You believe that? So you get more signal if you have high refractive index, the contrast will be higher, the cross-section will be higher. But in terms of how fast it moves...
it's like getting a larger DC shift in your signal, essentially. And the background signal will be high.
Yeah, so the ratio of that will kind of be constant.
I guess a related question would be, is there a rule of thumb on what your refractive index of the medium should be in relation to the particle itself for you to even get a signal?
So that depends on the sensitivity. Of course, at the asymptotic limit where the particles have the same refractive index as the medium, you don't see them. So you want that contrast as high as possible, basically. That's a simple rule. That will give you more signal. Any more questions? We're okay? Okay, this was the briefest review of dynamic light scattering, but hopefully we got the ideas. All right, thank you. So let's come back in about 10 minutes.